Hello, everyone. My name is Swagat. I'm a postdoctoral research fellow at the University of Nottingham, and this is an absolute pleasure to be talking to you today for the Cosmology from Home 2025. I'm going to talk about probing inflation and post-inflationary dynamics using inflationary gravitational waves. So let us get started. Now, over the last 3 decades, our understanding of the early universe has improved quite a lot, in particular using fluctuations of temperature and polarization of the cosmic microwave background, and combined with Big Bang nucleosynthesis and a plethora of very precision large scale structure data, we have understood that structure in the universe forms by starting from very tiny precise fluctuations in the early universe. In fact, the early universe was in a state of hot and dense plasma phase. Okay, and we have also understood that it is strong hint evidence that there was an epoch of cosmic inflation. It's a period before this primordial hot dense plasma phase, which kind of provides initial conditions for the hot Big Bang uh, universe. That's the topic that I will be talking about today. So let's understand. In particular, we have tracked down the origin of initial fluctuations very well by now. In particular, we have understood that the large scale structure of the universe has formed starting from tiny temperature and density fluctuations which were present in the cosmic microwave background via gravitational instability. And we can further trace back the origin of CMB fluctuations to a primordial initial fluctuations, which I am calling it zeta here, which I'll define shortly. And the properties of these primordial fluctuations has been traced down pretty well. For example, the fluctuations are adiabatic in the sense that fluctuations in dark matter, in baryons, in photons, in neutrinos, all of them were initially induced by a single field, which is zeta. On top of that, these zeta fluctuations to start with are correlated over length scales which are greater than the Hubble radius. So these are super Hubble fluctuations in that sense. And additionally, that the power spectrum of zeta fluctuations turns out to be almost scale invariant. In fact, you can approximate it roughly as a power law of this form, where there is an amplitude which is very small, and a scale dependence through this tilt here, ns minus 1, and the tilt also turns out to be very small. So whatever physics created these original fluctuations, it's more or less a scale invariant physics. Okay. And furthermore, the probability distribution function of zeta turns out to be predominantly Gaussian. There may be small deviations from Gaussianity, but so far all the observations are consistent with having zero non-Gaussianity. So it's predominantly Gaussian with a kind of standard deviation, which is roughly about 10 to the power minus 4. So great. So these primordial fluctuations can be naturally induced or naturally sourced by quantum fluctuations during cosmic inflation. So now we have this modern or extended standard model of cosmology. So the hot Big Bang phase is actually not the beginning of the universe. We think that this is actually the end state of the previous period of accelerated expansion, which is inflation. So we think that there was a period of accelerated expansion, which is inflation, and at the end of it, the energy that was driving inflation got dumped into all the particles of the standard hot Big Bang model through this period of reheating. And then once we're into the hot Big Bang, then the standard cosmology progresses. So radiation domination, matter domination, dark energy domination, and so on. And this epoch of reheating, which going from inflation to the hot Big Bang, is supposed to be the origin of all primordial matter in the early universe. So that's an important epoch. Now, coming back to inflation and talking a little more about it. So cosmic inflation is a transient period of accelerated expansion in the very early universe. In fact, it would have happened at a temperature which is greater than 1 mega electron volt, so very early times. And you can think that it's a transient accelerated epoch, and you can source it by using a scalar field condensate, which comes to dominate the early universe. And it's almost smooth. And the condensate has a self-interaction potential of some shape, and the condensate rolls down slowly. It means that everywhere in the universe, the inflaton field value decreases slowly. And during this period, universe goes through a quasi-exponential expansion in which its scale factor uh, grows exponentially, and by the time inflation ends, universe expands by at least e to the power 60 times. So I'll call it e folds, so 60 folds. Okay. And then once inflation is over, the inflaton field reaches its minimum and it oscillates and then it decays. And then it creates the standard hot Big Bang. So it heats up the universe to the hot Big Bang phase. So that's the standard picture. And at the end of inflation, universe is quite smooth and spatially flat. So that's the background universe, initial conditions for the background universe. On top of that, quantum fluctuations during inflation, which exist at small scales, are being constantly stretched due to the accelerated expansion. In particular, the co-moving Hubble radius during inflation falls, and after inflation is over, the co-moving Hubble radius increases. So tiny fluctuations which are much below sub-Hubble, they are stretched to go outside the Hubble radius, where they remain frozen. So one by one, they leave the Hubble radius during inflation, they remain frozen, and one by one, they enter the Hubble radius slowly and try to move the plasma, and that's how they induce the origin of all structure in the universe. Today, I'll particularly focus on single field slow roll inflation. This is a very successful framework. It just assumes that there's a single scalar field which sources inflation. And in fact, the simplest model is that the scalar field in standard general relativity, it couples minimally to gravity, so which is described by this simple action, gravity and scalar field. And the space-time metric is roughly a Friedman-Robertson-Walker metric. So it's roughly homogeneous and isotropic with some fluctuations present. Okay, and in particular, there are two types of fluctuations which are important as an observable in the late universe after inflation is over. And those two types are, the first one is a co-moving curvature fluctuation, which is my zeta, and it's built out of the 3D Ricci curvature fluctuations, psi, which appears here, and the inflaton fluctuations themselves. So this is a gauge invariant quantity, and it's important observable. These zeta fluctuations induce all temperature and density fluctuations in the primordial universe. On top of that, there are unavoidable transverse and traceless tensor fluctuations, HIJ, which is here. And these tensor fluctuations after the end of inflation propagate as primordial gravitational waves. Okay. And in the standard inflationary picture, often for most shapes of the potential, there is a slow roll regime in which the inflaton field changes very slowly and it moves in a slow terminal speed. Such a slow terminal speed is usually quantified by two slow roll parameters. One is epsilon1 and one is epsilon2. Epsilon1 tells us, if epsilon1 is small, it tells us that universe is expanding almost exponentially and the inflaton speed is very small. And if epsilon2 is small, it means that inflaton speed is small and almost a constant. So it's a terminal slow motion. Okay. Now, under these slow roll approximations, it is easy to use standard quantum field theory to compute the inflationary fluctuations. In particular, here I'm showing you the calculation of scalar and tensor power spectrum during inflation. The scalar power spectrum turns out to be dependent on the Hubble parameter during inflation, which is roughly a constant, and the first slow roll parameter, while the tensor power depends on only the Hubble scale during inflation. Both scalar and tensor fluctuations on large cosmological scales can be approximated to have this kind of power law form, where there are these amplitudes and then there are tilts. The scalar tilt depends on both first slow roll parameter as well as second. And since both are small, so the tilt is small, so they are nearly scale invariant. The same thing goes for tensor, but it only depends on the first slow roll parameter. Okay. So an important quantity regarding the amplitude of fluctuations is the tensor to scalar ratio here, which depends on the first slow roll parameter, and that's also small. So in this sense, if the scalar fluctuations are small, then tensor fluctuations are guaranteed to be small. So inflation creates tiny fluctuations that are nearly scale invariant as far as I'm talking about slow roll inflation. Okay, great. Now the exact predictions for the values of the scalar spectral index ns and the tensor to scalar ratio r or any other quantity really depends on the shape of the inflaton potential. And in general, inflaton potential could be some monomial potential that could be either convex or concave. It could be like a symmetry breaking potential, it could be a action potential, or it could be an asymptotically flat potential. So it comes in many different shapes. Okay. The details of the shapes don't matter. The details of the functional forms of these potentials do not matter for today's talk. But what I want to say you is the following. Now, taking into account recent observational constraints on inflation, particularly from Planck and Bicep Keck, we have measured the scalar amplitude very, very well. It is 10 to the power minus 9 and it's small. We have also measured NS, the scalar spectral index, which is 0.965. So NS minus 1 is negative and small, so nearly scale invariant. And the tensor to scalar ratio has not been measured yet. So we haven't seen any tensor fluctuations so far, but we have an upper bound which says that tensor fluctuations are at max 3.6% of the scalar fluctuations. Now, in particular, this final bound leads to the fact that Hubble parameter during inflation is at max 10 to the power 13 GeV, and the energy scale of inflation is at max 10 to the power 16 GeV. So these are very nice constraints. On top of that, if you combine both NS and R constraints, then we get that most of NS is contributed by the second slow roll parameter, while the first slow roll parameter is at least an order smaller than the second slow roll parameter. So this is a very nice new hierarchy, and I won't be discussing much about it here, but I'll be very happy to talk about it during the conference. It's important. So here is the observational plot. This is tensor to scalar ratio plotted as a function of NS. And this gray shaded region is where the 2 sigma observational plot is located. And all of these dots and colored plots are different theoretical or potentials or models, basically, predictions of different models. And you can see that all convex potentials are basically ruled out given the data. And concave potentials are strongly favored. So a typical concave potential is this, which sort of flattens. So the time when the CMB fluctuations were created, the inflaton field's potential better be concave. Now, usually these plots, the theoretical predictions are plotted for both 50 and 60 e-folds, assuming that the fluctuations that you see in the CMB left the Hubble radius about 50 e-folds before the end of inflation or 60 e-folds. Now, this 50 and 60 is not some magical number. It could vary and change between even 40 or 30 and 70 or 80. Depends on the details of post-inflationary evolution. Today, I will not talk about it, but I would be happy to talk about it in the conference. Okay, now let's take home message. Given the current data, latest data, single field slow roll model of inflation works very, very well. And the data favors concave potentials, and a representative class of these concave potentials are these asymptotically flat potentials of this form. Okay, let's keep this in mind. A small but important aside is that the Atacama Cosmology Telescope have released their data in 2025. And in Cosmology from Home, this year we will have a proper dedicated discussion on the ACT results. But here, let me just mention that both the Planck satellite, which is an all-sky mission, and ACT, which is focusing on a given patch of the sky, they probe different multipoles of fluctuations. For example, Planck goes from multiple number 2 to 2500, which belongs to a range of co-moving length scales. And Planck says that NS is roughly about 0.965 with some spread depending on 2 sigma or 1 sigma. Similarly, ACT probes higher multipoles or smaller length scales or smaller angular scales, and that's about 600 to 4000. And so it looks at higher co-moving wave number or smaller lengths. And ACT results indicate that NS is roughly about 0.974. So it indicates towards slightly more scale invariant spectrum. And we could discuss more about it. But I'll focus mostly on the Planck results in this talk. Okay, that's great. So inflation explains the quantum fluctuations during inflation explains the origin of structure in the universe very well. However, we know that the early universe was in a hot, dense plasma state, so inflation has to get over, and the universe needs to make a transition to the hot Big Bang phase, and that process is the inflaton decay and reheating. To discuss about reheating, let's talk about what happens to other fields during inflation. So data favors single field slow roll model. That's nice. So secretly, we have been talking about the cold inflationary paradigm, which means most of the energy content of the universe is in the inflaton field, not in other fields. But there may be other fields present in the universe. On top of that, the couplings of the inflaton field to other fields, these couplings are also assumed to be small and negligible in the sense that here is a typical fermionic coupling, and here is G square is a typical phi square chi square to another boson, another scalar field coupling. Both G square and H are supposed to be very small so that whatever little particle production happens during inflation, they're quickly diluted away by the exponential expansion, so you can neglect them. However, no matter how small the couplings are, they do have important effects on the dynamics. For example, inflaton coupling during inflation leads to higher point correlations or primordial non-Gaussianity, which is a very important topic and would be discussed in cosmology from home. The other important fact, which is particularly relevant for this talk, is that after the end of inflation, when the universe is not accelerating anymore, then particle production can accumulate, and then it can heat up the universe to the hot Big Bang phase, which is the epoch of reheating. Now, I will not talk about reheating in detail in this talk, but I want to summarize some of the things that we have learned in the last few decades. In particular, we have understood that if the inflaton field has a coupling to another bosonic field, is the simplest form, and if the coupling parameter is not extremely small, it is reasonably large, then the offspring fields chi grow almost exponentially. And this happens in bands in the sense that some momentum of the offspring field are produced exponentially and other momentum are not produced at all. So this is a highly non-perturbative effect. It's called parametric resonance. Now this may happen at the very early stages of reheating, right after the end of inflation, when the inflaton condensate begins to oscillate. At late times, the decay is more slow and perturbative in the sense of standard Feynman type of decay. Also, if the couplings are low enough, then always the decay would be perturbative. Now, the third thing is that if the couplings are ridiculously small, then this inflaton decay process can last for a long, long time. So the transition from end of inflation to hot Big Bang could last for a long time, during which the inflaton condensate would keep oscillating coherently everywhere, unless gravitational instabilities would kick in at very, very late times. Now, that was supposed to be the standard norm few decades ago. And as the inflaton field oscillates, if it has a stable minimum, a massive minimum, then it behaves like basically non-relativistic matter. But this seems to be not correct in light of the latest data, because the shape of the potential is concave, which means the potential can be written as a primarily quadratic part at the minimum and a minus something, which is basically because of the flattening. And this negative sign just tells you that the inflaton has attractive self-interactions, which means whatever quantum fluctuations, small quantum fluctuations of the inflaton field, they can start to clump by self-interaction and they will form lumps. These lumps are called oscillons. They are a type of cosmological solitons, and they are highly long-lived and highly robust nonlinear structure. So universe might become dominated by oscillons after the end of inflation. Now, it's an important topic on its own, but let me just summarize what we have learned about oscillons. First important thing is that oscillons form from generic initial conditions at the end of inflation. You do not have to do anything. As long as the potential is flat enough, oscillons would form eventually. Then recently we have found that oscillons also form when the inflaton field has an external coupling to some chi, let's say. And for a reasonably strong enough coupling, even then you can form oscillons. So what we have found is that the post-inflationary dynamics could be very, very complicated. You may come up with a model, a particular model where inflation ends, reheating happens, and the universe goes into hot Big Bang in a very simple and quick way. But for most models, the post-inflationary dynamics is complicated. Now let us zoom back a little bit and let's think of the broader picture of inflation. Now, what is need to be done in the next 2 decades? I believe inflation can be thought of as three different areas of study. the more formal and theoretical study, phenomenological as well as observational and instrumentation wise. Now, theoretically, there are many questions. What is the origin of inflaton field, single field or multi-field? What are the exact interactions of the inflaton field? And what are the formal ways of computing inflationary correlation functions? Now, all of these topics have been discussed in Cosmology from Home in the previous editions, and they might be discussed in this edition too. Now, phenomenologically, the fluctuations that we see in CMB, whether Planck or Atacama Cosmology Telescope, they only belong to about 7 to 8 e-folds during inflation, the early stages of inflation. The rest of the 50, 40, which whatever is left over, e-folds, are not constrained by observations. So it may have interesting small scale dynamics, which we don't know of. And that is another topic which has been discussed in Cosmology from Home many times. And then, of course, by understanding primordial interactions, we should also compute primordial non-Gaussianity signals for the next generation CMB and large-scale structure observations. And again, this is a huge area of research and very important area. But today I'm going to focus on inflationary tensor fluctuations and the subsequent gravitational waves. It has something to do with the way inflaton field decays and reheats, and basically the post-inflationary epoch. And this can be sort of probed by both B-mode polarization of long wavelength tensor fluctuations in the CMB and gravitational observatories for short wavelength inflationary tensor fluctuations. So let us state another important thing before moving forward, is that for as early universe physicists, one of our fundamental goals is to discover new high energy physics from early universe. And in general, cosmological correlators are our important observables. And the way we should think about these correlators are the following. The observed correlation function depends on both the initial fluctuations, let's say inflation created them, and their subsequent time evolution, which depends on how universe has been expanding in between inflation and you observe. Okay. And so it's sort of convoluted between both of them. So we call it transfer function initial conditions. And by understanding one of them, we will have information about the other. So cosmological signals could be of the form of non-relativistic relics like helium nuclei, or could be primordial black holes or cosmological solitons, or they could be propagating signals like cosmic photon background, cosmic neutrino background, or today I will talk about stochastic gravitational waves from inflation. Huge range of energy scale after inflation remains unprobed at present. So it's sort of in between 1 mega electron volt to all the way to 10 to the power 16 giga electron volt. And it would be nice if we can probe this energy scale by using, for example, I'm going to say that we can probe them using inflationary gravitational waves. So let us now focus on the main theme, which is tensor fluctuations from inflation. So during inflation, this tensor fluctuations quantum mechanical are stretched to super Hubble scales, and the tensor field has two polarization, plus and cross, so it can be written as combination of plus and cross. The tensor action actually is very, very simple. It's just a massless field, basically, two copies of massless scalar fields, basically. And there is an expansion factor because universe is exponentially expanding. And it's sort of relatively simple to use standard quantum field theory to compute the power spectrum of tensor fluctuations. And it was done by Starobinsky in 1979. And he found that the result that I have already stated, the tensor power depends on Hubble. And if you fit it as roughly a power law form, then the tilt is minus 2 times epsilon 1, which is minus tensor to scalar ratio r by 8. But r is pretty small from observations, so the tensor tilt is really small. And so for all practical purpose, we can ignore and think of tensor fluctuations being almost scale invariant. Now, these are at the end of inflation, these tensor fluctuations are created on super Hubble scales. And after inflation is over, universe starts to expand in a decelerating way. And so one by one, these frozen tensor fluctuations start to enter the Hubble radius. And once they enter the Hubble radius, they propagate as gravitational waves. So from now on, I'll talk about gravitational waves after inflation is over and after these fluctuations enter the Hubble radius and propagate. So inflationary output of tensor fluctuations is fed into the hot Big Bang phase through this epoch of reheating. So inflation, reheating, and then the standard radiation and matter domination. We don't know what happened during reheating, right? But these tensor modes, once they enter, they could enter during reheating, they could enter during radiation domination, they could enter during matter domination. But once they enter, they would propagate as primordial gravitational waves. It is very similar to scalar fluctuations. Once they enter, they propagate as CMB fluctuations, acoustic waves, and eventually that becomes the large scale structure. Okay. Now, since I don't know what happened during reheating, if I assume that during this post-inflationary unknown epoch, let me just call it unknown epoch, if the equation of state is a constant equation of state, I call it W, then I know how universe was expanding in terms of this W. Then the tensor modes propagating in the post-inflationary universe can be solved analytically in terms of two Bessel functions with two unknown coefficients A and B. Okay. And these unknown coefficients can be calculated because we know the output of inflation. So that acts as an initial condition. So then I know the tensor mode functions basically. Okay. These are your strains of gravitational waves. If we measure on large scale B mode polarization of CMB, that will tell us the tensor amplitude on large scales, which is related to the energy scale of inflation or the Hubble scale during inflation. That's great. Now, in most of the studies, you would usually assume that right after inflation, the universe became quickly and immediately radiation dominated. While this is possible, this is a very special assumption. It can happen in some models. But generically, reheating is a complex process and it will take some number of e-folds before you can transition into the final radiation dominated epoch. So early universe is expected to go through a number of distinct epochs before it becomes radiation dominated. And since the inflationary tensor fluctuations or gravitational waves propagates through all of these epochs and comes to us, so by measuring its amplitude and tilt, we will be able to measure what was going on around that time. Okay, this is not possible with photons because they're coming from the last scattering surface, not from before. So I hope that's clear. Now, observationally, the quantity that is important for us for tensor fluctuations is the so-called spectral energy density, and that's the energy density of gravitational waves per log frequency band, and then usually scaled by the critical density of the universe. Okay, and this could be computed in terms of the strains or the tensor mode functions. Basically, I give you all the formula here just for completeness, although I would not be needing it in this talk. So I'll jump ahead and tell you the final answer. The spectral energy density of gravitational waves at any time tau is a conformal time, for gravitational waves of any wavelength k or any wave number k is k square by a square h square times the tensor power at that time for that mode. And the tensor power can be computed from the mode functions. So by knowing the mode functions, you can compute the spectral energy density. Usually the spectral energy density plots are not shown, so I thought it would be nice to show it in this in Cosmology from home. So here is a scenario where universe is expanding in this way from left to right. Here is the unknown epoch where I am assuming the equation of state is 0.8 just for illustration. Then the standard radiation domination, then the matter domination. I'm talking about three different modes, three different wavelengths of gravitational waves from inflation. And the dot shows the time when they enter the Hubble radius. Okay, so outside Hubble radius, the mode functions are frozen. So from there, you can compute what is omega ZW, and they're all parallel. Now, the one that enters during the unknown epoch, or let's call it reheating, then it evolves in certain way during the reheating epoch. Then it remains almost constant during the radiation dominated epoch, and then it falls during the matter dominated epoch. Similarly, a different wavelength, slightly longer wavelength, which enters during radiation domination remains flat, and then it falls in the matter domination, and so on. You can basically track each and every wavelength through the time all the way until today. And then you can calculate what it is today. Talking about today, we need to calculate the present day frequency of these gravitational waves. Now, the present day frequency of these gravitational waves can be related to the energy scale of the early universe at the time when the frozen tensor fluctuations from inflation entered the Hubble radius and started propagating as gravitational waves. So this is the energy scale when they started propagating as gravitational waves. Okay. So if it is 1 GeV, very early universe, then that will correspond to roughly 10 nanohertz frequency. Okay. So let's see some of the examples. At the beginning of Big Bang nucleosynthesis, the particular mode which was entering the Hubble radius has the gravitational wave has a frequency of 10 to the power minus 11 hertz. So very long wavelength. Something that was entering during QCD phase transition has about few nanohertz. So you can see them through pulsar timing array, which is here. Similarly, something that was entering through during electroweak phase transition has a sub few microhertz frequency. So that's basically LISA. So you can probe electroweak phase transition using LISA. Finally, something that was entering at very high energy, more than 10 TeV, has a frequency of sub-millimeter. That, for example, could be probed by the LIGO or the future Einstein telescope, etc. So gravitational wave detectors or observatories are basically high energy physics detectors. And that's our great scope to discover new physics. Okay, so now if you compute the spectral energy density, all the way, you evolve them all the way until today, you will find that those tensor modes or gravitational waves which were generated during radiation domination, or they entered the Hubble radius during radiation domination, they have a spectral tilt, which is the primordial tilt, which is very small. So they're basically flat. This is the high frequency or short wavelength fluctuations. So this is the unknown epoch before reheating, before radiation domination and after inflation. If the equation of state of this unknown epoch is some W in general, W reheating, I'm calling them W, then the tilt is twice W minus 1/3 by W plus 1/3. So if W is exactly 1/3, then here also the spectrum will be flat. If W is soft, the equation of state is soft, which means it's smaller than 1/3, then the tensor fluctuations or gravitational wave spectral energy density is suppressed. While if W is blue tilted, if W is stiffer, which means greater than 1/3, then the inflationary gravitational waves would be blue tilted. So they'll be high and they can enter your detector. And in fact, if reheating happened or the transition to radiation domination happened at late enough into the universe, and if the equation of state is stiff enough, then the signal can rise a lot, and in fact it can violate the Big Bang nucleosynthesis constraints. So it might lead to overproduction of gravitational waves. Okay, great. So a question was asked in this particular paper, which was a very brilliant work, that what's the equation of state of the unknown epoch after inflation, and what is its duration, so that you would see a signal in the LIGO or LISA. So that was asked, and they actually determined the parameter space. So it's a very nice work. And of course, the conclusion was that equation of state should be stiff, okay, and reheating should be low enough, but not very low, because otherwise it will lead to overproduction of gravitational waves. So that's great. However, I spent a bit of time stressing the fact that reheating dynamics is extremely complex, first of all. So the expansion of the universe may change as reheating progresses. Now, on top of that, the early universe might go through a number of phase transitions. To give an example, even in the standard model of particle physics, here is the energy scale that I'm showing is about 6 orders of magnitude energy scale. There are 3 different epochs in which the equation of state of the universe deviates from purely radiation-like equation of state, which is 1/3. So it deviates from 1/3. For example, this is the electron-positron annihilation. It drops. Then it's the QCD phase transition. It drops by about 30%. Then this is the electroweak phase transition, where it drops again. Okay, so if it can drop during standard model dynamics, as we go to higher energy, there will be more dynamics beyond standard model, and it may go through multiple epochs of change in equation of state. On top of that, early universe may become dominated by topological defects and moduli fields and other degrees of freedom. So the early universe, the equation of state of the early universe is extremely dynamic. And so probing the first 3 minutes of the universe has been a major global effort, basically. And I give a review paper on that topic here. But since the early universe could be complicated prior to radiation domination, it is more natural to model the early universe. Uh, it's more natural to assume that the early universe was composed of a number of distinct epochs with different equation of states. Just like the late universe, you go from radiation domination to matter domination to lambda domination. Similarly, in this work, we took the view that the early universe before radiation domination consisted of many distinct equation of state. To make it a little more precise, we assume there are many different equation of states and universe makes transitions between these different equation of states. To remain model agnostic, we did not assume the exact values of equation of states. Okay, so we said after inflation, there's an epoch of W1, then there's a W2 and so on before you finally become radiation and standard matter domination. Now we carried out our analysis by the following assumptions. The first thing is we assume that the transition from one epoch to the other epoch is instantaneous. This is for analytical computation to be possible. So initially it was W1, then it dropped to W2, it jumped via theta function, then to W3 and so on. So then what we can do is we can compute the tensor modes at each epoch separately because we know the analytical solution and then match at the boundary by Israel junction conditions to get the full mode functions. Then there is a second assumption which is not necessary but is important is the following, that we assume that the tensor to scalar ratio generated at the end of inflation is at least 0.001 so that you could see these fluctuations on large scales using B mode polarization of within the next decade. Let's say Lightbird can measure up to 0.001 and Simon's Observatory will also work very soon. So under these two assumptions, we ask the question, what is the parameter space like W1, W2, W3 and the duration between each epochs so that the inflationary tensor fluctuations would lead to observable gravitational waves today by any gravitational wave observatory that you would like to focus on. Okay, so that's the question we asked in this work. So here is how we first computed the tensor mode functions. The tensor mode functions are represented in terms of Bessel functions, and there are two unknown coefficients. The first epoch right after inflation, for that epoch, the unknown coefficients are easy to calculate because you use inflationary output as the input for the first epoch, and that these are basically the initial conditions, and that completely fixes these two coefficients, so you know what is the tensor fluctuation in the next epoch. Now, after that, there could be many subsequent epochs. So you solve them in different epochs, and then you assume the continuity and differentiability of mode functions, and that leads to junction matching conditions. And so now you can completely determine all such coefficients. Okay, so that's you're going from inflation via number of epochs during reheating to final radiation and matter, and you can match all of these mode functions in between to calculate today's mode function, which is what you are interested in. Let me just show you how the results look, although it's not important. Here is the tensor mode function at any epoch at a given time of a given wavelength k, and that's Bessel function with two unknown coefficients. The unknown coefficients of a subsequent epoch is related to the unknown coefficients of a previous epoch via this simple linear relation. Okay, so see that we could do this calculation purely by hand. Of course, we checked it with Mathematica and Python, but this was a sort of beautiful piece of calculation. Now you use these tensor modes to compute omega GW, which is your observable, and I just wanted to remind you its formula, so I have written it again. So you calculate this quantity from the mode functions, and then evolve it until today, and then plot them. So here are some of the results. These are 4 plots. this has one unknown epoch of an equation of state W1. This has 2, W1, W2. This has 3, W1, W2, W3, and there are 4 here. Okay. Now, when you have one epoch, unknown epoch, I have chosen in this plot to show that W1 is 0.73 just for illustration. Okay, it's not necessary. And just to be consistent in all 4 plots, I have chosen that reheating ends at about 1 GeV. You don't have to assume that. This is just to show in this plot. So you see that if you have a long epoch of stiff matter domination, then you have a high rising signal which can barely enter LISA here. It can enter Einstein telescope without touching LIGO and without violating Big Bang nucleosynthesis constraints. Similarly, if you have 2 epochs, you can enter LISA, you can enter Einstein telescope safely, no problem. Then you may have 3 different epochs. And more importantly, you may also have a peaked spectrum, like here in this 4 different epoch picture, you have an inflationary gravitational waves, which has a peaked spectrum. Okay. So it's not that if you have any stiff matter domination, you would violate BBN constraint. Even for a low reheating temperature and stiff matter domination, you can easily avoid Big Bang nucleosynthesis constraints. At the same time, you can enter different detectors. Okay, so let's ask that question. So what parameter space would be detectable via particular detectors? That's what has been shown here. So this is 2 different equation of states before radiation domination with one transition in between them, which is 100 GeV, just for illustration. And this gray patch is Big Bang nucleosynthesis constraint, so you cannot be here, otherwise you will violate the constraint. The rest of the light colored patches are different gravitational wave detectors, and you can see that if W1 is high enough, greater than 0.2, and W2 is high enough, greater than 0.1, then you would necessarily enter the bands of these detectors. So you'll have a signal there. I saw a similar thing here with a slightly higher transition energy, which is 10 to the power 10 GeV. Okay. And this red color is when you enter LIGO band, because LIGO hasn't seen any stochastic gravitational waves. So this is also ruled out. But then there is this parameter space, which leads to a future gravitational wave signal. So this is for illustration, but the actual details are there in our GitHub repository. And if you want to use our calculations for your model, you can see this. Okay, now we have been model agnostic so far. However, we did apply our techniques to a particular model, which is string theory and the first half of the universe paper by the Oxford and the Nottingham group. I think Joe Coleman talked about it 2 years ago in Cosmology from Home. So following inflation, there is a phase of kination in this model, in this scenario. So equation of state is +1 after inflation. Then there is a radiation domination, transient radiation domination, 1/3. Then as this is a moduli field, and as it oscillates, universe goes through a transient matter domination phase, and then this moduli field decays and reheats, and universe becomes finally the standard radiation dominated phase. So the shape of the signal is here. It's the kination signal, and then radiation domination, then matter domination before the final standard radiation domination. Okay, so you can easily avoid Big Bang nucleosynthesis constraints, at the same time entering inside some of the detectors in the future. We did calculate the range of parameters which will lead to a signal in the future detectors. We also know the range of parameter space, which is ruled out by, let's say, Big Bang nucleosynthesis constraint. So you can actually already put constraints on different parameter space of models. Okay. Now that was assuming that the tensor to scalar ratio is high enough so that the signal will be detectable by a B-mode polarization of the future CMB detectors. However, if you relax that condition, then if tensor to scalar ratio is very low, then no matter whatever is your reheating temperature, you will not see anything. So the shaded region is something that you will not see. Okay. So only detectable region here is this white color small patch. And that makes sense because if tensor to scalar ratio is small, then it's difficult to have a signal. Okay, now some ongoing and future work that we want to now apply our techniques to some concrete phenomenological scenario instead of being model agnostic. And we assumed our transition to be sharp or instantaneous in the previous case that I discussed. That's good for Bayesian kind of analysis, but to be realistic, all transitions would be non-instantaneous or smooth. So we have started working on how to deal with smooth transitions, and this will be a complete numerical work. Um, in this talk, I talked about inflationary vacuum fluctuations, vacuum tensor fluctuations. But if by any reason at small scales you have large density fluctuations, then at second order in perturbation theory, it creates the so-called scalar induced tensor fluctuations. And one could also in principle study the spectrum of scalar induced tensor fluctuations propagating through a universe which has multiple equation of state. Okay, that hasn't been done. Other thing I ignored are the gravitational waves which are produced during these unknown epochs, during preheating, reheating, and maybe other phase transitions in the early universe. Okay. So therefore, there will be a plethora of different signals at small scales, which could be detectable by various gravitational waves. And the big question, the ultimate question would be how we could break the degeneracy between different signals. Okay. So this is a global effort in the community of primordial gravitational waves. So I think the future for inflationary gravitational waves in particular and primordial gravitational waves in general could be very exciting. We have a plethora of different observatories coming up within the next 1.5 decades. So let us see what we discover about the early universe. Thank you so much.